Hi, I'm Paweł Spychalski and today let's do some science. Yes, no matter if we like to admit that or not, our hobby, the RC hobby and especially the multi-rotor part is really very tightly connected with actual science. Really actual science, not some hobby, but it's really working only because of the science and something called the control theory. Control theory, that is the part of the science when very smart guys think about how to use the computers, how to use the mathematical processing as MCUs, MPUs, actuators, sensors and different stuff like that to really precisely control the behaviors of the physical system. Because yes, our drones, our aeroplanes, our multirotors, boats, whatever really we have out there, if we are using any kind of destabilization, we are controlling the very precise state of those systems. This is part really of the control theory. And probably the most important and also kind of not correctly understood part of the control theory, it's something called the PID controller. Because really, trust me, when I say that misunderstood, I really mean not misunderstood. The science guys really tend to explain what the PID controller is in a so hard and not obvious way that if you just look at this equation, you're like, oh, but how does this apply to our cases? On the other hand, when the RC hobby guys try to explain what the PID controller, not all, not everyone, I have to say, no, there's quite a good examples, they really kind of omit some of the kind of important caveats of the whole problem. Today, in this video, I will try to explain to you what is the PID and PIDFF controller, because feed forward, which stands for FF, is also part of the control theory, and we will do it in the most simplistic way around without using any equations, just saying step by step and remembering after some of the caveats of the whole problem. So let's begin. If we are talking about the control theory and the PID controller, the name, we will explain the name slightly later, you have to understand that the PID controller works only if there is a feedback loop somewhere there, where the physics is applied. That means we have the measurement phase when we measured the current state of something, like for example in case of the multirotors, we measure the angular velocity by the gyroscope. We have the control part when we try to determine what kind of the output, what kind of modification to the current state should be made to meet the requirements. And we have the actuator state, the actuator part where something physically changes the behavior of the system. In our case, this is motor propeller and the ESC when they change rotation and thus change the force distribution and change the angular velocity in all the three axes. And we also have the physics part that puts some kind of we have to say a noise into the whole process, because it puts the noise, it puts the inertia into the process and quite a lot of other minor differences that make that what comes of the actuator is not really the same thing that comes into the measurement part, in our case the gyro. But it's about everything. We can work with temperatures, we can work with distances, we can work with, I don't know, linear velocities, we can work with position, displacement, flow, why not, current, anything, only in our case it's usually the angular velocity. Now, when we know what the feedback loop is, there are three terms that everybody has to understand. The term number one is the measurement. Yes, the measurement is something that goes out of the sensor, like the gyroscope, thermometer or flow meter or the anemometer or whatever else. And this is the information about the current state of the system. In case of the multirotor drone, it's the information how fast it's rotating among one of those axes. this works in degrees per second. If this is the high rotation, if this is the low rotation, and is this close to what we set this should be rotating or not, This is the measurement. All the filtering, all the actual measurement is part of the measurement phase, and measurement really is the information about the current state of the system. There is something called the set point. Set point is our input. This is our desire of what the system should be doing. In our case, RC Hobby, we are, with the position of the stick, we are telling the multirotor drone, rotate right, for example, with a speed of 100 degrees per second, or do not rotate, stop the rotation, keep the current rotation rate at 0, and thus keep the attitude, the inclination, or this is the inclination at this given angle. That's all. This is the information. This is the user input into the whole flow of the control, in this case the PID controller. And then comes the error. Error, Error, of course, is the difference between the measurement and the set point. If the error is 0, that means that the state of the system is exactly what we want this. If, for example, the set point is 0 and the measurement is 0, that means the error is 0 and everything is a-okay. Probably there is nothing or very little that should be done to keep the system in this very specific state. It's not completely true, but we are getting there. And now we go into the question, what is the PID controller? The PID stands for proportional, integral, derivative. If you do not know the exact meanings of those three words, you can check it somewhere. For example, in the Wikipedia. Let's begin with the proportional part of the PID controller. The proportional is very often referred to as the P term. You know, it's shorter version, and everybody, yeah, P term. Do not have to say, oh, proportional. No, you can say just P term. P term has a very simple goal. The P term tries to keep the current error at 0. This is exactly what the P term does. If the current error is above 0, then it tries to lower this towards the 0, and if it's below 0, then it tries to raise it towards the 0. P term only keeps the current, in this very specific moment, error at 0. At least it tried. How? By multiplying the error, and we already know how to measure error, by gain, which is usually called the P gain. That means error is 7, for example 7 or 42, doesn't really matter, and the gain for that is 3, then we measure 3 times 7 or 42, output is 21, and 21 is put into the actuator. If actuator then converts the information 21 into some kind of the physical state, then it's either fine, it's either too low, either too high. If the P gain is too low, then our system, in our case the drone, multirotor, will not be able really to keep current angles and will be like drunken, will be doing a drunken sailor. If, however, the gain will be too much and the response of the system will be too high towards the demands, it will be overshooting, then overcorrecting. It will go into this characteristical, relatively high frequency oscillation. So, not enough P means that we are wobbly and not able to keep the correct state. Too high, too much of the gain of the I term, that means we are going into the oscillation. Very important, with the current modern multirotors, the oscillation from too much of the P are really hard to observe in the level flight. You really have to push it to feel it, because we really improved quite a lot of things. Still, the rule applies. To mechanical response, P is usually too high, not able to track the error, keep it at 0, then probably the P gain are too low. Next we go into the I term, the integral part. And the role of the integral part is very simple. It's super simple. It tries to keep the history of the errors at 0. I term is almost completely ignoring the current error. It doesn't work with the current error, it works with the history. What does it mean? That means that internally, every time we go into the I term computation phase of the PID controller, we multiply the current error times a very small number, usually much smaller than the P gain, and add it to the previous. So we keep the history how previously in the past the error was behaving. And thanks to this, the I term is able to know if our system usually goes left or usually goes right. Think about this like that. If the center of weight is not equally in the center of thrust, or for example the propellers or motors on the right side of the multirotor are slightly stronger. That means even with the exact output from the system for all the motors, the ones on the right side will be always creating a slightly more thrust and will be always rotating into the left. With the I gain and with the I term, the controller learns from the past experience, accumulated error on the accumulator, that we usually rotate slightly left, and that means that usually the motors on the right side should be getting slightly less input to really have the level information and do not do crazy stuff into the air. That's all. What's happening when the I gains are too low and not enough of the history is brought into the current state? Then the controller usually is unable to keep the level. When you tilt it to the left with the command of the stick, then it will then go into middle position, or it will be slightly similar to the P term, but happening slightly lower. The simplest way to test the I gain, I term on the multirotor with the FPV, you just put it into the level flight and see if over time it will level out or it will it will make the angle on the pitch bigger or better. If it's keeping the angles, then it's probably fine. If on the other hand the I gains is too high, then some kind of the oscillation might happen, but usually this is not so obvious to observe because you really would have to overshoot the I gains very much to observe something like that. However, too much of the gains means that the I term can accumulate, can wind up, and then when you finish the maneuver there will be too much. But we have things like I term relax or I decay in IMU flight to counteract those kind of things. And with those mechanisms in place, we usually do not really have to worry that much about the too much of the I gains, because there are fail safes into the process. So it's there. And now we go into the derivative, the so-called D term. And many people say that D term thinks about the future, how the system will behave in the future, and dampen something. No, the D term really has nothing to do with damping. Well, it kind of damps, but damping is not really what D term is doing. D term is keeping the acceleration at 0, because with the D term we compare what's the difference between the last step and the current step, and we take only this difference into the consideration. We compute the acceleration, not the error, but we compute the acceleration. Of what? It can be either acceleration of measurement or acceleration of set point, of acceleration of error. It's really, there are different approaches to what D term should be doing, and should D term be working with measurement, or if the D term should be working with the error. It really feels then different in the error. There's a different kind of level of response comparing from what you are computing the D term and the acceleration, still D term always tries to keep the acceleration at 0. If the D term then is computed from the measurement, then the D term always indeed acts like a damper, because when you start the maneuver, start the change, it will try to counteract it and do not allow the object to accelerate. If the D term gain, of course, is too high, then it might overdump it, and if it's too low, then on the other hand, the response can be very mechanical. When it's not like slowly accelerating towards the set points, you have this very mechanical, rapid movement. The same thing, by the way, is happening when at the end of the maneuver, when we release the stick, how then the response should be handled. Should be the more or less damped response or very rapid stop. This is also driven by the D term. But still, remember, this is only working with the acceleration. On the other hand, when the D term is computed from the error, then it changes the feeling, because it's not always damping. Sometimes it's even accelerating, making the feeling slightly more how to say it, mechanical. Still, but we will not be really going into the details of how the D term based on error or acceleration works. That really makes no sense right now. Please do remember that currently the most popular flight controllers, like for example Betaflight and also the ImuFlight, not the INAF by the way, is always computing the D term from the measurement, and then yes, the D term is always acting as a damper. Then there is also this feed-forward element. And what's the difference between the feed-forward and all the others? Feed-forward does not take the measurement into the consideration at all. It only acts with the set point. We say rotate 100 degrees per second to the right. What it does, just multiplies the 100 by some kind of gain and puts this to the motor. It completely ignores the current state of the system. It has some advantages, it has places where it makes sense. You can also work with the derivative of the set point for the feed-forward. There are really a lot of different approaches for solving this problem, and we will not really go into the details, because I can probably shoot a whole 1 hour video only about the things with the feed-forward, and this really makes no sense. So feed-forward works only and only with the set points, completely ignore the measurements. In Betaflight, it acts like the accelerator of the movement, so that the response is not always swooshy and soft. If you really move the stick, then a derivative of the endpoint is treated as the feed-forward component. Complicated, never mind. And then, when we know what all those three components are doing, let's go into the final view of the problem. How this is all combined together, like this, like what you are seeing right now on your screen. We have a sensor which takes care of the measurement phase, and we have the user input. This little circle with the X is the thing that computes the error, and the error is passed into the P term, I term, and the D term. It's not 100% true, because it depends on what the D term is working, but almost. I didn't want to make this chart too complex. All those three components are outputting some kind of the number, and the same happening with the feed-forward, which ignores the current measurement, only takes the set point. There is some operator which just adds three of them and applies this to the physics part by actuators, like for example motors, propellers, or a heater, or a valve, or a fan, or anything, and this works with the feedback loop and once again puts the information on the sensor. Okay, the video is already slightly longer than originally I wanted this video to be, and I really hope that I made the whole explanation what the PID and PIDFF, or just PIFF controller really is and how it works, because without understanding how the PID controller works, it's really bloody hard to tune it. If you do not understand how something is working, then how are you going to tune it to the behavior you want this to present itself? So I really hope that it was simple enough. I really tried not to use too many equations and not to make this overly complicated. I do intend to make quite more videos with those slightly more technical aspects, like for example, what the fuck is a mixer? And why do we have a mixer? And what does the mixer does? And more about filtering, but this is for the future. For today, thank you for watching. If you really survives this more than 20 minutes of me talking about the PID controller, I really have to say you're tough. You're tough. Yeah, kudos for you. Until the next one. Bye bye.